My name is Doug Oldenburg. I'm a professor at Earth and Ocean Sciences. And this class is, what is it, 50 something? So I haven't seen you for a while, but you look familiar. Okay, so pick up hopefully where Devin left off. We're looking at ground penetrating radar systems. The physical property is electrical permittivity, which we kind of translate into dielectric constant. The understanding about the dielectric constant, there was a really nice kind of motivational thing with respect to microwaves. Everybody kind of get that, understand how a microwave works. Go home, talk to your parents, whoever. Understand why put a potato in the microwave actually works. Good. Yeah, the physical properties are also affected by electrical conductivity, which causes attenuation of the signal, and to some extent magnetic permeability. I think the thing that makes ground penetrating radar one of the easier components of the course is the fact that we've already had a lot of stuff that is similar to this when we do the seismic. So you're kind of familiar with wavelets and you're familiar with the seismic section, and the radargrams look pretty much the same. In fact, you can think about them in almost exactly the same way. The only thing is that in one case you've got an electromagnetic signal, and in the other case you had an acoustic signal. So I think Devin took you through virtually all of the base work. I want to maybe just review a little bit of that, and then going to talk about a couple of issues and some a couple of examples, and that should actually wrap this up. So you've seen this a number of times. We've got a transmitter, we've got a receiver. So there's an electromagnetic signal that goes down and back up to the receiver. Electrical physical property of primal importance is the dielectric constant, and we see a radargram which kind of looks like sort of like a seismic-gram. We've got distance this way and we've got time this way, sometimes converted to actual depth. And we often tend to see sort of layered structure, which is indicative of layers. And we see hyperbolic structures that are reflectors, so maybe they're tanks or tunnels or something like that. The pulse looks something like that. It's a kind of a band-limited sinusoid. It's got a particular length, delta t, and that's then intimately tied in with the resolution. The transmitter and receiver in this case are just in this little box. So the higher the frequency, the smaller the antenna that you need. So you can actually make these things really quite small, and for very high engineering purposes, you can have things that are just really small boxes, and you gradually get larger. You can have a number of different kinds of acquisition systems. You could have a common offset, which is usually the one that people do. So here now the receiver and the transmitter are separated by a fixed distance, and then you just move along like that, and you get reflections from the subsurface. Or you can have a common midpoint system where the transmitter and receiver get symmetrically moved about some midpoint, so you kind of get a reflection off of one point. So that's the way we're thinking more for the seismic case. You can do transillumination, where you've got a transmitter on one side of something and receivers on the other. This could be a gallery that you're trying to figure out what's inside here, or you could also do a borehole to borehole. So there's lots of applications that kind of fit into these different methods of acquiring data. Some of the important things that you should now take away is the relationship between the frequency of the transmitter that we're working with and the actual signal that you're getting out. And there's a couple of things that are really important. If the if your transmitter operates only at a very small bandwidth of frequency, so this is in the frequency domain, and if you have just a small localization here, then that means in the time domain we have an extended pulse. So they work in reciprocal. A narrow band in frequency gives a wide band in time. And then if you kind of looked at the envelope of this, it would sort of look like that. As you make this frequency band larger, so extend this outward, then this shortens and you get maybe something that looks like that. And here's your envelope. And then if you make it really quite long like this, then you can get a very contracted compact signal. Looks like that, and that's in space. And there's a number of ways of thinking about the wavelength of it. It's basically the wavelength is the velocity divided by the frequency, which when we convert it to the ground penetrating radar, velocity was the speed of light divided by the square root of the dielectric constant. So that gives you one idea of what the wavelength is. The center frequency, this guy here, is related to the time length of the signal. So that gives you basically 1/t. And then you can put everything together like that. So that gives you a relationship for the wavelength and the center frequencies. And then a couple of things that were important was that there's always this compromise between resolution and probing distance. At higher frequencies, you get better resolution. There was two types of resolution that Devin, I think, talked to you about. One was vertical resolution, so kind of finding delineating a thin bed to see if you could determine the reflections from the top and the bottom. And that kind of came out to a formula that looked like this. The other is if you've got two pipes or two objects that are separated by some distance and they're at some particular depth below you, then how far apart do they need to be before you can actually see them as two independent objects? And that was this formula here. The one thing about the higher frequencies, however, so higher frequency gives you smaller, it gives you better resolution. So everything is divided by frequency. However, increasing in frequency also causes the waves to be attenuated more quickly. So there's a kind of a depth of investigation that you can find, which is basically 3 times delta, which is called skin depth, and it depended on whether sigma was greater than omega epsilon or sigma was much less. But anyway, so these are formulas that you could use for kind of saying, okay, how far can I actually probe into the ground? And then you've got also information about resolution. So that's great. You start off with a system, you want to have these concepts about depth that you can probe in and your resolution. So the things for then today, I want to just talk very briefly about converting travel time to depth, and also talk about noise reduction, as well as some interpretation examples. So here's something that you'll see. So here's your radar ground. It's taken in terms of time, which would be two-way travel time. Very often they will attempt to put another label on this side, which is depth in meters. And of course, in order to do this, you need to have some velocity. In reality, the Earth is probably a whole bunch of different layers, but they'll often just try to convert with a simple representative velocity. So you might try to think of what the average dielectric constant is for the region, and then use a velocity of c divided by the square root of that, and then give you that velocity. And then you could use this formula that the apparent depth is equal to whatever velocity you got times t divided by 2, because t is always a two-way travel time. So take this t, which is two-way, divided by 2, multiplied by v, and then that gives you a depth scale on here. So that's nice. It kind of calibrates then what you're looking at. I'm not sure what Devin talked to you about, but there's, as these waves are traveling through, then they reduce in their amplitude because of spherical spreading and because of just attenuation that comes about from electrical conductivity and scattering. So what that means is that if you start off with a big pulse, as it goes into the ground, its amplitude decays and will continue to decay. And if you just plotted the trace as it comes back to the receiver, you might have something that looks like this. So there really actually is signal in here. You can see this guy here, but he's so small in amplitude that you can't see him on this plot. So what we'll do is to take this trace here and just multiply it by a function that continually increases with time, and that just sort of raises up these amplitudes. So every radargram that you will look at will always have some kind of, it's called gain. So it's just a way of taking whatever trace you've got and multiplying it by some function, that progressively increases in time. So if you do that here, so here's that function, if you can see it. It sort of comes up like this, and then it only comes up to a certain maximum number, and then they just leave it. And then if you take this and multiply the trace here, then you get something that looks like this. So now we can see these, we can see all of the pulses that are coming up in here, and this little guy that was sitting back here is really quite observable. So what that gain is done individually within the transmitter and receiver geometry, but there'll always be some kind of a gain function that's supplied. The other thing is that there's always going to be a lot of noise that's going on, and we saw previously, back here, that the signal strength is actually pretty small, right? So if you have something that's kind of blurred into the thickness of this line, you might start to worry that maybe just the noise is going to come and corrupt it. The good thing with the GPR systems is that they actually require many representative pulses in a fairly short amount of time. So these things are operating at megahertz to gigahertz, and that means that you can easily create hundreds of thousands of samples within a very short amount of time. So I mean, you can still be pulling the system along as you're walking, which is generally what they do, but everything is happening so fast that you're maybe doing 10 or 100,000 traces that you're stacking just in the time that you're walking like this. So the idea with stacking, as you're probably really well aware, if you take random noise, so if I had a signal buried in here and you just add random noise, then it looks kind of mucky. But if I take a number of realizations of this with the same signal, but different noise, so if that background noise is Gaussian, and then if I sum them up and take an average, then I reduce that noise by, anybody know? If I add up a whole, if I've got n traces, or n samples of something, but I have Gaussian random noise that's got some particular standard deviation, let's say sigma. If I now take n samples of this guy, then how much do I reduce the noise by? What's the factor? Anybody? Whatever square root n? Is that Ring a bell? Not many bells. Okay. So if every time I take, you'll have a chance to do this in the lab. So you'll take a signal and add noise, take the same signal, add another realization of noise, another, and then you add all of these guys up, take their average, and what you'll find is that the noise level progressively goes down and the signal comes up. So that's what's happening here. If you use 5 stacks, then you can see how things have decreased. So the amplitude of this noise is now reduced, so by a factor of 1/5. And then if I had 20 stacks, now you can see that it's reduced even more. So the standard deviation here is maybe 1/√20 of what it is there. So that's one way of reducing the noise on your final trace. The other way, since we're actually sampling very quickly, we're sampling so that there's many sample points in a particular period of the basic wavelength, that we could actually go along with some kind of averaging of 5 point or 7 point or what like that, and just sort of run a smoothing average over the whole trace. And then when we do that, we also get a better signal. So here's again that initial trace. We just do a 5-point average or a 10-point average, and again you see how this signal that you've got is coming up. So these are kind of processing things. We've got gain, and then we've got some kind of noise reduction, which either comes about from the stacking or just averaging. Well, I guess I should have asked the question. Actually, this is what I really liked about these particular slides that that Devin put in, which is both the recapping and the question. So here was the main points, that we need the gain correction, stacking is reduced, and we could do increased stability just by averaging of the amplitudes. Basically what I just said. Yeah, okay, so here's 2 questions. First one, why would we do a time to depth conversion? Yeah, it's an easy question. I mean, times don't mean anything, not really, especially when you're talking about things that are traveling at a fraction of the speed of light. So you need to have some kind of a calibration. And, then the second question is, what are different ways to reduce incoherent noise? Stacking and smooth things. So if we are going to use this, I mean, one of the first things that you will see when you're kind of working with a contractor, maybe they've done a GPR survey over here, and maybe you got something then that looks like this. So the contractor gives you this. And then what we're trying to get across here is a little bit of how you think about things, what the context is that you want to use to kind of understand what's going on here. So there's a number of things. There's the survey, and there's the data, and there's an interpretation part. So it's worthwhile to kind of look at each of these. So if you're given something like this, here's your radar ground, then what are some of the things that you're really interested in? I mean, first of all, you've got an axis along here that's got some numbers. So you need to know whether that's in feet or meters or what that is. You've got time down here, so you need to be sure you know what that what that time is. You also want to know what the acquisition system is. So if it's a coincident transmitter receiver, you want to know that, or if there's some transmitter receiver separation, what is it? So you need to know something about that survey. The other is what the frequency is of the system, and that then also determines what the wavelet pulse width is. Because the wavelet pulse is going to tell you something about your resolving power. So that's really, really crucial. And so you want to know, was this a 1 gigahertz system? Was it a 100 megahertz system? Those things are really important. You'd also want to know something about the location and the physical properties that you're doing things at. In particular, conductivity is really important because that tells you how things are going to decay. So if you've got really low conductivity, you've got good penetration. If you've got high, then you can't do very much. And you also want to have some idea of maybe what the dielectric constant is. So that's going to, okay, what are the ranges basically for the dielectric constant? Anybody?
0 and 1?
Nope. So that so the dielectric constant, which is also called the relative permittivity, is the true permittivity over epsilon naught, that of free space. So these numbers are kind of big, and 10 to the minus 12 are really complicated numbers. But this guy here in air is going to be what?
1.
It's going to be 1. And then what's the other elephant on the block here for water? Right. And what's the dielectric constant of water? 80. Yeah. So that's basically where you're looking at the permittivity goes between 1 and 80. So if you've got some idea about what that is, that helps. And also, whether you've got, the ground is dry or saturated, something to be. You also want to know perhaps a little bit about the sort of the general characteristics of the ground as to whether there might be a lot of cobblestones or things like that, which would cause a lot of scattering. And actually, that is kind of interesting too. If I think I've got a bit of time to digress, in Switzerland, they worry a lot about rock glaciers. I've asked people, and they have some here in British Columbia. They're not an immediate big hazard, but there is the potential. So you've got the side of a mountain, and then you've got a region in here in which there's just kind of ice and rock. And so if you walk over it, it probably looks a little bit like rock. Is there anybody here that's kind of a alpinist and knows about rock glacier? In Switzerland and in Europe, they're worried quite a lot about these things because they can, just mobilize and slide down. Okay, good. So now they want to do some big surveys on here, try to find out what these, what the composition looks like in here, and also where this bedrock is at depth. So they have this really good idea. So let's go across here with a ground penetrating radar system and see what we can see. And when they got the radar grounds back, it's just a hodgepodge. It was just stuff that was all over the map. Couldn't make any sense out of it. So what they then did is decide, okay, well, maybe what we should do is actually, instead of having a system where we're really right up close, we'll actually go a little bit farther away and run with a slightly lower frequency that would lose resolution, but maybe have penetration down. And what they did when they did that was that all of these scatterers that, if you're really right close to them, they have tremendous signal. But if you go farther away from them, they're not so evident. And simply by taking the system, moving it away from all the scatterers and changing the frequency slightly, they were actually able to get really good images. So the kind of knowing what the complexity is of the structure and how much scattering you have can be important. And then the ever important question, sort of what kind of resolution and probing distances might you expect? So that's on the survey. And now if we go to the data, so now we've got this, then some questions that you might ask are, what's the earliest time that you can measure? You notice when you're looking at the radargrams, there's always like a big signal that's sitting right up at the top. That's a very, very complex environment. You've got your transmitter waveform and the instrument and that connection with the ground. It's a bit of a hodgepodge, and it's very, very difficult to invert that or to understand exactly what's going on here. However, once you get away from that, by the time you get to these things down here, and especially down here, you can see that, okay, I've got some really good signal, and I can start to make some sense out of this. So what's the earliest? You can see, you can kind of tell. What's the latest? The latest depends on kind of where you are. So the latest signal in here is up over here, and the latest signal here is actually getting down lower. So there's something different that's going on both sides. And then other things that you might look for are, do you have these hyperbolic shapes in here, which are scatterers, and then do you have sort of continuous layers that you can see, and perhaps sometimes you might even be able to see a sign reversal between a couple of reflections. So you can, if you have them distinct enough, you can tell that one is a positive reflection, the other is a negative. So in one case you're increasing in the dielectric constant, in the other case you're decreasing. So then when you're going to interpret, I kind of made a comment about this. You've got hyperbolic signatures. The interesting thing about hyperbolic signatures is that you can go ahead and use the apex to kind of tell you where things are. And if you've got a nice tail on here, you can get the velocities of the medium. And importantly there, you can tell if the velocity is the speed of light, in which case it's actually something that's sitting up on the surface, or if it's at a reduced velocity, it's probably something that's happening in here. Yeah, then are there linear features? Are they dipping? And yeah, are you able to get signal from beneath the reflector? If you're actually able to get signal from beneath the reflector like this, then you know that the electrical conductivity is not completely damping things out. Whereas what you see up here is that we've got a real loss of energy, and this region up in here is being caused because you've got high electrical conductivity. So as the waves come down, they just attenuate through. But over here, we're actually able to kind of get through at least to a certain extent. So I just want to take you through a couple of quick examples. So this was the one that we did on the very first part of the course. So we've got that example on this traverse through Ireland, where one of the cases was to try to find the thickness of the peat. So we've got this peat layer, and the instrument was a ground-penetrating radar system. So it's attached, it's got this little tractor here, and here's your GPR system, and we've got a way of locating where this thing is as a function of time. And this is a 100 megahertz GPR antenna. So it's a common offset survey. So we've got fixed transmitter receiver, operates at 100 megahertz, and the data have been collected, and there's going to be a time to depth conversion. And there's also going to be one processing that's being done just to correct for topography. So in the end, and I'll show you why this is. So suppose that we had a topography that looked like this. So, and let's suppose we've got a flat line, interface down here. So now we're going to come along and we're going to do our GPR, our survey. So we're going to be right up on here. And then we're going to be looking at, the two-way travel time back to here. So at these various places. So A. So that's what's happening geologically. But what's going to happen when we do the radar? So if we now do the radar, so remember all we're plotting here is time and then X location here. So at point A, so the students all want velocity. At point A, the travel time is this distance divided by the velocity and then times 2. So that's a big distance. So that means that the time at which that reflector comes in is going to be big. As I come along here to point B, it's a little bit less. As I come to point C, it's considerably less. And then D is greater. So in fact, if you then looked at the radargram, right, you would see that, here's your trace, and then you got this thing here, right? So it looks like this, which is exactly the opposite of what's happening geologically. So that's the one processing step that you want to recover. And so what you need to do for that is just to figure, okay, what's your topography relative to some location, and then find out what that travel time distance is and adjust for it. So that means that you need to know the topography, and here is the topography without a scale, but it's topography. And we take that, and here is this is the radargram, so it looks like this. Right? So here's your, so if you're actually to look at that, if somebody just showed you the radargram, you'd say, oh, wow, that's really, there's a lot of stuff that's going on in there. But in fact, there's not a lot of stuff going on in there. The topography actually looks like this. And now if you do that correction for the topography, then what you see is that all this stuff here now lines up on a straight line, which geologically is probably right? So you had a flat line layer down there, and then you got stuff that was scooped up top. So geologically, this makes sense. And then you come back up into here, and there's something else happening up on this direction. But if you try to make a geologic interpretation by just looking at that picture, really wrong. So that's an important, I think, takeaway message here, to make sure that when you're looking at this radargram, if there is any topography, it's been taken into account. Yeah, so here is an example in a potash mine. So now 0 is at the bottom. The reason for that is that so it's like this is the mine workings up here, and there's the ceiling, which I finally figured out is called the back. Anybody else know that? What is the back of the mine? I always thought the back was there, but the back is up there. And so now you have to put the instrument on the ceiling, which you can see it's a bit of logistics. But now you're sort of coming across like this, and then you get a radiogram that looks that. And what you're looking at here is trying to see if you can find where there might be water. If there's a layer that suddenly has a fair bit of water, it's going to give you a nice strong reflection. And if you look at this particular image here, you can see that there is a very strong reflector that comes up here about 7 meters above here. So you're down here, you're looking up, trying to see if you see something, and you've got a reflection. If you just have time here, okay, time is interesting, but as we talked about earlier, you really want to convert to some kind of depth or distance. Depth, that way. So the question is, what might your procedure be to try to make that conversion? How do you, what are the things that you need to know and how might you get them? So if somebody just gives you this and you're in a potash mine, then you'd really like to attach a depth scale. And the question is, what your thought process might be to get that.
The velocity of the host rock.
Right, so we need the velocity, good. And then what might be your next thing? Well, it might, there's a number of ways to proceed, but one way is just, you not only need the velocity of the host rock, if you knew something about what that geologic formation was, okay, then we might be able to use some tables. So in our particular case here, we're in basically an anhydrite. Okay, so now you've got an anhydrite, and then you could go back and look at that initial tables that we had in the physical properties, and that would tell you that here's how you actually get that velocity of the anhydrite. It would come up as about 0.13 meters per nanosecond, and now with that you can then convert that. But that's basically the process. You've got from time, you need to have a velocity. How do you get the velocity? Try to figure out what rocks you have and look it up in a table, or that would be the easiest. Yeah, so the earliest return in the signal, what kind of features do you see? Across here, I think the main features that you see are this strong reflector, but you notice that it kind of zaps out occasionally. Right? So I think Devin talked about ringing effects. So there are places that you just get junk that comes through and it kind of distorts the signal. But so you've got this sort of interleaved, kind of ringing, probably from infrastructure that's coming in there, and then over here, then you've got the apparent distance to the water. So that would be the first order of what you get out of that, and actually that turns out to be very useful information. And again, things like this are kind of, well, they're kind of tricky, right? Because ordinarily you'd think, maybe the best way to figure out where this is just to drill in. But drilling into a water layer that's above you is probably not a good idea. So if you've got some way of remote sensing that's good. Another example, this was actually done a number of years ago by just a group here from UBC. So this is out just out of Pacific Spirit Park out here. And there's Camosun Trail for those of you who walk through there. The goal here was to do a traverse, and this was actually done. These were the days that the equivalent, or the predecessor to your course, actually went out and took data. So there was a line here, and they took GPR data across here, and resulted in an image then that looked something like this. So there's, oh, and that's the thing. So here, notice this is not all in one box. This is a lower frequency system. So you can see how wide the antennas are here. I think this was a 50 megahertz antenna. And so every time you reduce the frequency, you have to increase the length of the wires for the antenna. So that's why they're getting to be that size. And then one of these was a transmitter and the other is a receiver. So it was actually quite a nice system, and we still have that system here. And you can go out and you can collect data, and you can do all kinds of kind of interesting things with this, as far as turning the receiver around so you've got a different kind of coupling, and doing this common midpoint gather stuff. So it actually works. From the point of view of what we saw, if you look at this, there's something very distinctive that's going on here. There's a very nice, strong horizontal reflection here, and then it's broken up. So there's something happening right here, and then you've got something different. The other thing that's most noticeable is that you get signal that's coming back down to these particular times or depths on this side, and on this side they're kind of washed out. So our thought was that, well, maybe there's just really high conductivity here, and things are just being attenuated. So in order to get some information about that, we actually did another experiment. We did a DC resistivity experiment, which we will see towards the end of this course along this same line. We'll talk about this later, but this is basically the electrical conductivity section across here, with the red colors being conductive and the blues being resistive, so very low conductivity. So all of this now starts to make some sense, right? So somehow about at this boundary on this side, stuff just gets really more conductive. There is a nice layer that's going on in here. And as you come to this side, then it's more resistive. So there's certainly something that's happening right along that boundary, and we're getting deeper penetration. Just the last couple of quick examples. Perhaps one of the things, if anybody is doing, just kind of utility engineering, trying to find pipes or wires or something like that. Underground storage tanks, that's a real common one, especially with all these old gas stations around. Then you could use a GPR system. So the first thing that you want to do is try to figure out, okay, what's the orientation of the thing that you're looking at or that you're looking for. So if it's pipes, okay, then you want to be going perpendicular to these so that you have a chance to see them. If you go parallel, you're not going to be so successful. So there's a few things that you want to do, is to orient your survey as best you can so that you're perpendicular to what is you're looking for. And then you also need to worry about your frequency of your system. So if we've got a single tank, might be look something like this, so that helps try to on the location. And then remember this t squared x squared. If you get far enough away, then you just the slope is fine. That can give you the velocity, and then that gives you the depth. If you have a number of these, like basically a tank farm, then you might get something that looks like this. So basically, it allows you to sort of see the top of these guys, and it's very difficult to see anything that's that's underneath. If we come back to our kind of resolution studies for the tanks, if they were like a meter below the surface, not so much, and if you had an operating frequency of about 500 megahertz and you assume this as a velocity, then you could still have some chance of seeing these individual tanks if they're far enough apart. But to decide whether or not you're going to be able to recognize them, you have to go back to that formula of horizontal resolution. So in this case here, with that velocity that we've got here, the depth of a meter, the operating frequency, that gives you about 24 centimeters. So that means if you had two pipes that were 24 centimeters separation, and they were a meter below the ground, you might be able to distinguish them. If the pipes are fat, so that there's less than 24 centimeters between the outside edges, you're not going to be able to distinguish them, and it's just going to look like a horizontal, big, flat reflection. Yeah, so that kind of gives an overview. So just get to kind of sum up. We've got an electromagnetic method, electrical permittivity. The signals can get reflected and refracted. I didn't talk about refraction today, but Devin would have told you about waves that kind of come down, get refracted at the air interface, and the refraction occurs in the air layer and not underneath the ground. Generally, taught few meters, tens of meters. Someplace if you go out if you're in a desert environment, you can use these and get down to maybe hundreds of meters, or in glaciers, on ice fields, you can actually get pretty substantial depth. And the examples that can be applied to are actually quite wide. Geotechnical problems, infrastructure, pipes, storage tanks, near surface properties and structures. Golder uses GPR, for instance, a lot. Forensics, archaeology. It's actually been used to try to find bodies or things like that in avalanches. Possibility. So when you're planning the survey, there's just a couple things just to keep in mind. Like first of all, what do you know about the local physical properties? And importantly, how deep do you need to go? So what's the depth, and what are the dimensions? And that allows you to pick the grid spacing and the operating frequency of the system. And then you had a couple of formulas about vertical resolution, horizontal resolution, probing distance. Those are really the key things, because that's every time you kind of coming into have a particular problem, you cast them in terms of this, and then it'll tell you, like, okay, which system do I need to use? And there's always this compromise between resolution and probing distance. Yeah, so what to look for: hyperbolas, linear features, use the geometry, get layer velocities, and depths to interfaces. Perfect. Okay. Any questions? So that basically concludes GPR, and then we'll have a quiz, team-based learning first, and then a quiz for this week. And then next Monday will be kind of like a midterm review. So we just kind of rewind everything and just think about questions and look at things that might be on the midterm exam. And then we'll have the exam, and then we can be on to electromagnetics.